Okay, guys, looks like the quiz is timed out. As I was watching you guys' answers come in, people were doing pretty well with the one with the net ionic equation for the acid-base reaction. And remember, you don't have to spend time there because you might recall from the video that as far as you guys are concerned, the net ionic equation for every acid-base reaction is going to be the same. It's always going to be hydrogen ion combining with hydroxide ion to give you water. So regardless of what the acid is and what the base is, that's always what your net ionic equation is going to come out to be. And we'll see that again today as we go through one or two more of these. On the other one, make sure you guys are looking at your solubility rules and making sure that you're comprehending how to use that solubility rule table or chart that I gave you guys. So it's just practice, practice, practice. All right, so where I want to go ahead and pick up today is with acid bases, sort of leaning on what we did with the video from last night. And what I want to talk about is a specific application of acid-base chemistry, which is acid-base titration. So really all we're talking about here is just a reaction occurring between an acid and a base, just like we talked about in the video. Now here's the deal. What we're trying to do in a case like this is, for example, to determine, if you look at what I've got set up here, I've got a beaker down here at the bottom, which I'll point to. And inside of that beaker, I've got a 25.00 milliliter sample of sodium hydroxide. And notice I don't know the molarity of it. So the purpose of the titration is to determine the molarity of the base that's in the beaker. Now, up at the top, I've got a thing called a burette. Okay, so that's what that thing is that I'm showing you right here. And my guess is that a lot of you guys have done a titration of some sort or another, maybe in high school or here or wherever. And the idea is that we can open and close the burette in order to essentially monitor the amount of what we call the titrant, which is the liquid in the burette, going into the solution into which we are going to titrate. So we can control the flow of that liquid by opening and closing this thing called a stopcock there. Okay, so basically I can meter how much of that solution comes out of the burette at any given time and goes down into the solution into which we are titrating. So in the burette, I'm going to put, in this case, phosphoric acid. So that's going to be at a concentration of 0.1085 molar. Now here's the deal. What we're going to do is we're going to add the phosphoric acid from the burette into the base until we get complete neutralization of the base. In other words, I've added enough moles of the phosphoric acid to exactly react with all the moles of the sodium hydroxide I've got in there. And normally what we would do is we would put some sort of a colored indicator into the beaker. And what happens is that changes color right at that equivalence point, as we call it, where the moles of the acid are equal to the moles of the base. And when we see that color change, it tells us to stop titrating. So at that point, what we'll have is a volume of the phosphoric acid required to fully neutralize the 25 ml sample of the sodium hydroxide. So in our example, let's say that it took 28.34 milliliters to do that. Okay, so that's the volume of the phosphoric acid I had to add to the base to get the base fully neutralized, okay, so that there's no more hydroxide ion in the solution. And again, I'm looking for some kind of a color change from, say, an indicator to tell me when that has been achieved. All right, so that's more or less the experiment that we want to do. And again, what we're trying to determine from all of this is the molarity of the sodium hydroxide I've got down in the beaker. All right, so when we look at this, it's really just an acid-base reaction. So we're going to write it as such. And ultimately, we're going to come back around to solving for the molarity of the sodium hydroxide. But first things first, let's write down a balanced molecular equation for the reaction that's actually happening. Okay, so we have an acid, so let's go ahead and write that down. That's going to be H3PO4, that's phosphoric acid. By the way, we're not going to worry about naming acids in here. I used to do that in bonding, and then I realized it's not terribly important. So I'll throw names around so you can hear them, but that's not something I'm going to ask you to say, okay, if I have H3PO4, you guys going to have to tell me the formula is H3PO4, or tell me it's phosphoric acid. No, I won't ask you to do that. And that's aqueous, because all acids are. And the reason for that is because acids dissociate when we put them into aqueous solution. All right, we're going to let that react with sodium hydroxide, which is the NaOH. There's my base. That's also, as a strong base, that's going to be something that dissociates 100% in solution. And we talked about in the video, right? When acids dissociate, they give us hydrogen ion. And when bases dissociate, they give us hydroxide ion. And those are the ions that matter in a neutralization reaction. All right, so now those are our two reactants. Now let's go ahead and determine our products. Now the same thing happens here as happens in a precipitation reaction. We get what's called a double displacement reaction, where the ions just exchange partners with each other. Okay, so think about the acid here. Where does this thing actually break apart? Well, it breaks apart right here. Okay, so I make my 3 hydrogen ions and I get a phosphate ion. Where does the base break apart? Well, the base breaks apart right here. So I'll get a sodium ion and I'll get a hydroxide ion when that dissociates. So now the ions exchange partners, right? So it looks like now the sodium ion is going to go with the phosphates. Let's just write that, Na. We'll write PO4 here, and we'll come back and charge balance that here in just a minute. And then the other thing that's going to happen is the hydrogen ion is going to combine with the hydroxide ion, and that gives us water, but I like to write it as HOH because it helps me balance the reaction equation. Now that's a liquid, right? Now let's get the right formula for the sodium phosphate first, because we got to charge balance this guy. So you guys will remember from your polyatomic ions, the phosphate ion carries a 3- charge. Okay, so how many sodium ions do I need to balance out the charge on the phosphate? Well, first I have to remember what the charge on an individual sodium ion is, right? Anybody remember what the charge on a sodium ion is?
1 plus.
1 plus, very good. So how many of them am I going to need in my formula to balance out the 3- on the phosphate? How many sodium ions? 3. Very good. So I need to end up with a 3 plus here. To do that, I got to put the 3 downstairs here because I'm talking about a formula of a salt here. All right, and then the next thing we do is we go back and ask ourselves, okay, is that soluble or insoluble? What's a sodium salt? Sodium's a group 1A metal. So, all those group 1A metals are soluble. So we put an AQ down there. All right. And the next thing we got to do is balance the molecular equation, right? So let's see. I got 3 hydrogens on the left. Okay, and we're going to balance these as hydrogens versus hydroxides. So I've got 3 hydrogen ions on the left. I need to have 3 on the right. So I'm going to put a 3 out in front of the water here. Okay. All right, I got 1 phosphate on the left, 1 phosphate on the right, 1 sodium on the left. Oh, but I got 3 sodiums on the right. So I got to put a big 3 out in front here in front of the sodium hydroxide. Now balance the hydroxides. Looks like I've got 3 on the left and I got 3 on the right, so I'm good. Okay, so that's the easiest way to balance that reaction equation. Now we're going to come back to this one from the point of view of the titration, but let's go ahead and do an ionic and a net ionic for this while we're at it, just to get some practice there. Now remember what happens in an ionic equation. Anything that's got an AQ under it, we can dissociate. Anything that looks like an L or a S or a G or anything like that, we're going to leave alone. Okay, so the AQ things we actually dissociate. So look at the first one. We've got the phosphoric acid. So that's going to come apart into its ions. Now notice that I've got 3 hydrogen ions per phosphate. So I have to write that as 3H1 plus. I'll put an AQ down there. And now I got a phosphate. That's a PO4 3 minus. That's our polyatomic ion. That's also aqueous. Okay, go to the next guy. Looks like I got 3 sodium ions because that 3 carries through, right? And I've got 3 hydroxides. 3 again carries through, it distributes. And remember, guys, put those charges on those ions. That matters, right? So if Chem 101 or I or whatever asks you to give me an ionic equation or a net ionic equation, the charges have to be there. So don't forget about that. All right, so now we go over to the AQ, sodium phosphate. That's got an AQ, so it dissociates. So it looks like per dissociation, I'm going to get 3 sodium ions. Put the 3 out front now when it dissociates. Still an AQ, and I get a phosphate ion. That's still in solution. So I got to put an AQ down there. And then finally, it looks like I've got 3 waters. I'll just write it as an H2O here. You can leave it as an HOH if you want, doesn't matter. All right, so now anything that I can break up into ions, I have broken up into ions. So that's my altogether ionic equation, showing how all the molecular things actually split up if they have AQs next to them. Okay, any questions about the ionic, how I got from the molecular to the ionic before I go on? All right, good. Let's do net ionic. Now remember, to get to a net ionic equation, we look for spectator ions and we cancel them out. Okay, so the spectator ions are the ones that look the same on both sides of the arrow, right? So I've got the hydrogen ion there. Okay, where's the hydrogen ion? Well, it's tied up as water on the right, so I can't get rid of that, can I? Look at your phosphate. Does it look the same on both sides of the arrow? Yeah, I think we're good. Okay, so we can get the phosphates out of there. How about the sodium ions? Are they the same on both sides? Yeah, I think we're good there. Yeah, thanks. So we can get rid of the sodium ions. How about the hydroxides? Can I get rid of the hydroxides? No, I can't, because they're hydroxides on the left and they're tied up as part of water on the right. So I can't get rid of those. So now what I'm going to do is I'm going to write what I'm left with, which is now going to be 3H1 plus AQ plus 3OH1 minus AQ. And that's going to take me to my 3 waters. And that's a liquid, right? Now, the last thing I can do to simplify this is I can get rid of all those 3s. I mean, what I wrote there is absolutely correct. But now if I wanted to simplify it down, I can just cancel out those 3s. And what am I left with? Just H1 plus OH1 minus, giving me a water. Oh, yeah, that's the net ionic equation for any acid-base reaction. So we proved yet again that if I've got an acid reacting with a base, as far as this class is concerned, that's your net ionic equation. So that never changes. All right. Any questions about getting from a molecular through an ionic to a net ionic? Everybody good? All right. So what I'm going to do now is I want to go back and I'm going to recast the, or rewrite rather, the molecular equation, because I want to use it to work my titration problem here. So I'm just going to rewrite it here. So I've got an H3PO4. That's aqueous, reacting with 3 NaOHs, bringing my coefficients down. Okay, and then I'm going to make sodium phosphate. That's aqueous. And what did I say, 3 waters? And those are liquids. All right. So now, this is really just a stoichiometry problem where we got to make a mole bridge, right? So what we're going to do is go back up to our titration information and just write down what we know about each reactant. Okay, so if you go back up, we'll just look at it real quick. What's in the burette? It's 0.1085 molar H3PO4, and it took 28.34 milliliters to get to what we call the end point of the titration. So I'm going to write those 2 numbers down. All right, and if I remember correctly, it was 28.34 mils of that. All right, and I also had a known amount of the sodium hydroxide in the beaker. That was what, 25 mils. So I'm going to write that down. I'll just write that down over here, 25.00 milliliters of it. And I'm trying to get to the molarity of the sodium hydroxide. Okay, so that's my target. All right, so here's the nice thing. We always work from the standpoint of the thing that we can get to the moles with. Okay, so do you see anything there that I can actually get to moles directly with? Okay, well, take a look at the phosphoric acid. You guys might remember when we first introduced the concept of molarity, we said that volume times molarity gives us what? Anybody remember?
The mass.
It's not mass, you're close.
Moles.
Right idea. Moles. There you go. Volume times molarity gives you moles. Very good. Okay, so we're going to work from the standpoint of the thing that we can get the moles of, which is the H3PO4. All right, so I'm going to go ahead and start by just writing out the volume here. So it's 28.34 milliliters. Okay, but I got to change it to liters, don't I? Because remember, the units of molarity are moles of the stuff per liter of solution. So I got to get my volume in terms of liters. I'll just show it as an extra step here. So that's going to be 1 liter. I should be putting H3PO4 here, right? Because identity matters. And that's per 1,000 milliliters of it. Okay, so now mils of H3PO4 will cancel with mils of H3PO4. I've got liters. Now I can multiply by the molarity of the stuff. So that's 0.1085. And remember, I'm going to go back to my base units of molarity. It's going to be moles of the H3PO4. That's the definition of molarity per liter of the solution. That plane's been buzzing my house all morning. I think somebody's really enjoying this nice weather out here. All right, so 1 liter of it cancels with 1 liter of it. So we're good there. I've got moles of it. All right, but what is it I'm trying to find out about? I'm trying to get back to the sodium hydroxide, but now I got moles of the phosphoric acid. So now I can make a mole bridge, can't I? I can relate my moles of my phosphoric acid back to my moles of my sodium hydroxide with a mole ratio through that mole bridge. Okay, so now I know that the phosphoric acid has to go on the bottom. That looks like 1 mole of it, right? From the balanced equation. And for every 1 mole of the phosphoric acid, I'm using up what? 3 moles of the sodium hydroxide. So that's what goes on top. Okay, good. We're almost there. So notice what happens. Moles of the phosphoric cancel with moles of the phosphoric. Now I got moles of sodium hydroxide. But I want to get to a molarity of it. So I need a volume of it, don't I? So I got the mole part, I need the volume part. Oh, but wait a minute. I've got the volume of the portion of NaOH I put in the beaker. Okay, I used a pipette or something to measure that out very precisely. Okay, so I've got that. So let's just add that. But that goes in the bottom, doesn't it? So we'll put another conversion factor here and we'll just leave it in terms of milliliters. So I have moles in the top of NaOH. Now I need the 25 mils in the bottom. Not quite done yet, right? Because remember what molarity is. It's moles of NaOH per liter of NaOH solution. I've got moles per milliliter. So I have to have one more conversion here. It gets me out of milliliters and back to liters. So I know that for every 1,000 milliliters NaOH, I've got 1 liter of NaOH solution. Okay, so now look what happens. My mils cancel with my mils. What am I left with? I'm left with moles of NaOH per liter of NaOH. That's molarity, isn't it? So let's check our sig figs as we go. It looks like I'm good to 4. Now working through, I'm good to 4 in the molarity, good to 4 in the volume of NaOH. So it looks like I'm going to be good to 4 sig figs all the way throughout. So when I work this out, I end up getting 0.3690. And that's molar NaOH. All right, and that's going to be to 4 sig figs. All right, any questions about that, guys?
Professor, where is the milliliters for those first 2 values come from again? I forget.
Milliliters for the first 2 values.
Yeah,
so you're talking about these guys over here for the phosphoric acid?
Yeah.
The 28.34?
Yeah.
Go back up to your burette here. Okay.
Oh, okay. Okay.
So when I did the titration, this is actually the 28.34 mils is the amount or volume of the phosphoric acid I had to add to the sodium hydroxide solution to get to what we call the equivalence point or the end point of the titration, where all of the NaOH has been used up, right? So that's a number that would be given as part of a titration problem Either that or you do the experiment and find out what it is. But in a problem, it would be given. That was the volume it took to neutralize all of the sodium hydroxide that you had in the pot. Make sense?
Yeah, it makes sense.
Okay. Any other questions, guys? And again, this is really just a stoichiometry problem. It's just utilizing a mole bridge and mole quantities to go from something we know about over to something that we want to find out about. So that's really all an acid-base titration is. And that's the thing about these stoichiometric type problems is I can apply them to any kind of reaction we want. I could apply them to not only an acid-base reaction, but I could apply them to a precipitation reaction, right? So I could say, for example, if I had a molarity and a volume of 2 soluble salts, right? I could do a limiting reactant problem and I could figure out how much solid I make on the other side. So I can apply these stoichiometric tricks to pretty much any kind of reaction I want to apply them to. It's just the same old thing over and over again. And that's why it's a good idea to practice it, because it's just one of those things that we see again and again and again. And you'll continue to see again and again. All right. There's no other questions. Let's pop over and do a little bit of Chem 101 practice.
I have a question about the quiz.
Yeah, we can look at it if you want. Yeah, go ahead and ask.
The solid formed in the second.
Yeah, I'm going to go ahead and
calcium
I'll actually write
carbonate.
that one up for you if you want. Let me show it to you. Let me show it to you. I'm just going to jump back to the quiz so I can see what the problem was. Of course, that's the wrong one. That's okay. I'll get to it. Back in February's quizzes now. Here we go. That looks like it. So let's go over here and see what we got. Yes, it's this one. Na2, and then it's a carbonate, right? CO3 aqueous plus calcium nitrate, is it?
Yeah.
That's also aqueous. Okay. Now let the ions exchange partners and let's just see what we get. So let's see, that means the sodium has to go with the nitrate. So I'm going to make NaNO3. Okay, and let's just make sure the formula is right. Sodium's always a 1+, nitrate's always a 1-, so the formula is correct there. And then the other thing we're going to make is calcium carbonate. So I'm going to couple the calcium with the carbonate, CaCO3. Calcium's always 2+, carbonate's a polyatomic, that's always 2-. So I've got the correct formulas for both of those things. Now it's asking you whether or not you're going to get, well, I guess we have to balance the reaction equation if we actually make a solid. So let's determine if we make a solid, then we can come back and balance it. Now, going back to your solubility rules, I'm just going to pull my copy up here real quick so we can look at them together. Hopefully you have your solubility rules next to you. Just pull mine up so we're looking at the same thing. All right, so let's look at the sodium nitrate first. Okay, so sodium is a group 1A salt, metal, right? All group 1A metal salts are soluble. So we're going to put an AQ there. We don't even have to go beyond rule number 1 for that. But let's now apply our rules to calcium carbonate. Okay, does rule number 1, it talks about ammonium and group 1A salts apply in any way, shape, or form here? No, it doesn't, because neither calcium's a group 2. Now, we also say that we've got nitrates, chlorates, perchlorates, acetates, except for, okay, do any of those apply? Okay, well, carbonate doesn't show up there as an anion. So rule number 2 doesn't apply in any way here. Okay, and then rule number 3 applies to sulfates. We don't have a sulfate here, so we move on down. Rule number 4 says chlorides, bromides, and iodides are soluble, except, well, we don't have a chloride, bromide, or iodide here. So we move down to rule number 5. Now, rule number 5 has calcium in it, right? So it says that calcium hydroxides and oxides are soluble. Now, does it say anything about calcium carbonate?
Wait, is the hydroxide and oxides for each of them, each of the ions?
Yes. So that would suggest that calcium oxide would be soluble. Okay,
that's
calcium hydroxide would be soluble. But does it say anything about calcium carbonate being soluble?
No.
It doesn't. So remember if we kind of run out of all options by the time we get from 1 through 5, what do we have to assume about a compound? Is it soluble or insoluble if we run out of options here?
Insoluble.
Insoluble, because it says up at the top, solubility guidelines, salts of these ions are soluble. So if you don't have a direct rule that says it's soluble and we run out of options, oh yeah, we're putting an S down there, okay? So that's soluble. Now you go back and you balance it. So let's see, we got 1 sodium on the left, we need 2 on the right, so I'll put a 2 there. That gives us 2 nitrates. We got 2 nitrates, 1 calcium on the left, 1 calcium on the right, 1 carbonate on the left, 1 carbonate on the right. There you go. Yep, so, and I was looking at it and I'm gonna see whether I can actually see it. I think a fair number of people could actually get the right products, but like several people didn't put a state in there to tell me what it was. And looks like a few people actually put AQ after calcium carbonate. So it looks like 4, 5, 6, 7. 7 folks who got it wrong actually got close to the right equation, but just didn't get the right states in there. So again, this is where Chem 101, gets a little picky. So make sure you guys are catching that. All right, so let's go back, and does that help to see it and kind of explain working through it on the table?
Yeah.
Hopefully. Okay, good. All right, so let's pop back over to our in-class problems here. And this is actually going to work out about right. I think this one we're going to do is about 15 minutes. So this is acid-base reactions. Okay, so let's get that started. Let's see, did something funny here. I'll get going. Start, here we are. Yes, there we go, we're moving. Okay, so this is really just kind of practicing what was in the video, and I think there's like one titration problem at the bottom here. So watch out on number 3. That acid there is acetic acid. So notice that when it dissociates, so in other words, it loses that hydrogen out front. What are you left with? You're left with C2H3O2 minus, which you guys will probably recognize as the acetate ion from your polyatomics. So it just looks a little different, but that's all that's going on there.
Can we explore number 3?
Yeah, that's the one I was talking about there with the acetic acid. And we can look at it here. I can pull it up on my, so here it is. It's HC2H3O2. It's aqueous because it's an acid, and it reacts with, looks like strontium hydroxide. Also aqueous. Okay, now here's the thing. Acetic acid breaks up right here. And you can tell with sometimes you'll run into these organic acids. And this is kind of a little bit funny because you guys might remember last time I told you that if you see things that have like carbons, hydrogens, and oxygens and nitrogens and stuff in them, those tend to be molecular things and they tend not to dissociate. You guys remember I told you that? There are a few exceptions to that, and acetic acid is one of them, and all the families of organic acids are as well. But this is really kind of the classic one you see in this course. Now you'll see other ones if you go on to dynamics, that becomes more important in that course. But in this case, think about it as that first hydrogen there popping off, and what are you going to be left with? You're left with C2H3O21 minus. That's the acetate ion that you learned from your polyatomic ions, right? So you know that one can be a stable ion. So let's go ahead and just watch the ions exchange partners there. So we end up getting the HOH just like we'd expect. Okay. And then the strontium's got to get together with the acetate ion. So I'll make SR, and then it's going to be C2H3O2. Now let's get our charges right. Strontium always carries a 2+ charge. It's a group 2A metal. Acetate always carries a 1- charge. Oh, so it looks like I need what, 2 acetates to balance out the charge on the strontium. So I'm going to put a little 2 down there. Okay. And it's going to be soluble, I believe. We can go back and verify that. We probably should and see whether it's soluble or insoluble before we go any further. So let me pull up my solubility table here. I should have left it. Let's just go through our solubility rules and see if it says anything about strontium. Okay, look down here. It says, see if it's going to be a solid or not. Okay, is there any rule about strontium? It says calcium, strontium, and barium. I'm going down to, and is there anything about acetates up top? Okay, I don't see any general rule about acetates up there. I mean, acetate turns out to be a, like in the silver acetate case in number 2, it gets shown there, but okay, but normally it says that one's going to be an exception. But it says acetate here is normally going to be soluble, right? So you got nitrates, chlorates, perchlorates, and acetates are soluble with the exceptions of those 2. Okay, so remember, these are hierarchical, right? So if I have a strontium acetate, okay, then that's going to tell me that should actually be soluble, right? Or does it? Let's see. Okay. I think actually with strontium there, I think we have to use rule 5, don't we? Because that's talking specifically about strontium, and it says, okay, it doesn't involve the acetate. It says only strontium hydroxides and oxides are going to be soluble. So what are we going to have to, which rule is going to dominate, rule 2 or rule 5? Do you guys think?
Rule 2.
It's probably going to be rule 5 because it's talking specifically about strontium salts in rule 5. So it says the only strontium salts that are going to be soluble are going to be hydroxides and oxides. So I have to make the assumption here that the strontium is going to be insoluble because I think, yeah, that's talking specifically about that ion. So this is where that hierarchy comes in. So, okay, if we're talking about a specific strontium thing, okay, everything that strontium does is going to be insoluble except for hydroxides and oxides. So I think that's actually going to be a solid.
I just Googled it and it said it's strontium acetate is soluble.
Is it?
Yeah.
Okay, interesting. Yeah, that seems to be an oddball one because I would, by my solubility rules, I would say that because we're talking specifically about strontium in item 5, and it says only strontium hydroxide and oxide. What does CHM121 say about it? In other words, when you guys did the problem, did it turn out to be soluble or insoluble? I can read.
Soluble.
Did it have it as soluble here? Yeah, it sure does. That's interesting because that seems to be against my solubility rules here, unless I'm just misinterpreting. But yeah, usually when you get down in the hierarchy, when you see calcium, strontium, barium there, and it says only hydroxides and oxides, you'd assume that everything else. Well, I take that back because if you think about like barium chloride is soluble. I know that, for example, calcium chloride is soluble. So yeah, it must be rule 2 that dominates there. That's interesting because I wouldn't have interpreted it that way, the way this is written. But yeah, that's got to be it because I'm thinking about just other salts of like calcium that I know, like calcium chloride and barium chloride. Those are all soluble. But then again, yeah. So yeah, that must be part of the hierarchy then. Okay, so I'll put an AQ after that. It's not how I would have interpreted it, but I guess I see that. All right, so how about balancing this thing? What do we got here? I've got one hydrogen, one. Okay, it looks like we need a 2 out front here. 2 hydroxides, so it looks like I need a 2 out in front of my water there. I think everything else is good. Yeah, that must be the way to interpret that. It's got to be that hierarchy. That's weird. That number 5 is confusing there. All right, let's see how we're doing here, guys. Okay, good. Yep, you guys are getting the titration problems as well. That's good. All right, so we got about a minute or 2 left. So let me just sort of prime you for what to expect on Friday then. So on Friday, we're going to start into the last kind of reaction that we're dealing with, which is called the redox reaction. So this is a type of reaction that involves a transfer of electrons between reactants to form new products. So we're going to start with the video, and the video will show you how to identify a redox reaction. And then on Friday, we're going to learn how to balance them. Balancing redox reactions actually is a little different from the typical way of balancing reactions that we've been using. So we're going to introduce a new way to balance reactions when we deal with those. Also, keep in mind, we got a Friday quiz coming up. So look back over the material from the last week, which is pretty much going to be it's going to be precipitation and acid-base reactions, maybe with a little bit of stoichiometry thrown in. Okay, so that's probably where we'll focus for this time's Friday quiz. All right. Any other questions, guys, before I head out? Okay, get outside if you haven't. It's beautiful out there. And I will see you guys on Friday.